Hi guys, today's lesson is about light and specifically talking about color. So in the entire electromagnetic spectrum, right, the huge spectrum, right, spanning 1800s and before, right, that has been established, we're talking radio waves down to gamma radiation. So we're talking low energy radio waves to high energy gamma radiation. Well, if we focus in just on the teensy tiny part of the entire EM spectrum that is visible light, right, that's the color part, right? And it's the visible, we call it the visible part of the spectrum, visible light, because it's what our eyes can see. Every single color that we observe has some slightly different wavelength, which is then associated with a slightly different energy. So looking at the spectrum at the bottom of the slide here, we see that red has the lowest frequency with the highest wavelength, capping at about 750 nanometers. And then we go towards violet on the left-hand side here, shortest wavelength, gets to about 350 nanometers, which then gives it the highest energy. So red has the longest wavelength, it has the lowest frequency, so it has the lowest energy. Violet has the shortest wavelength, so it has the highest frequency, so it has the highest energy. And it follows Roy G. Biv all the way down. So red, then orange is the next energetic, then yellow, then green, then we've got a little cyan in there, then we got some blue, right? So that's indigo if you want to get real technical with it. Now, white light, the way that we perceive light from a luminous object, which is something that gives off light, so anything that is white light, or even if it reflects and we see something that's white, it's every single wavelength of every single color combined, right? That is what white light is. Something that appears black is the absence of light. That means it is either absorbing every single wavelength of light or it is not giving off any light, right? That's black. Black is no light, where white is all light combined. Then we can break light down into being either monochromatic or polychromatic. The prefixes there are really important. Mono means one, poly meaning many. So if we have monochromatic light, that's going to be a pure frequency, a pure wavelength that is only going to be one specific color that we're looking at. Polychromatic light, if we start combining wavelengths, that's going to produce polychromatic. So technically, white light being all these wavelengths would be polychromatic. Now, the way that our eyes perceive color here, right? So light comes through the pupil and then it passes through the lens, right? The lens is going to bend that light and try to get it to focus towards the fovea. Sometimes that lens is not shaped properly based on your eye, or it's too strong, or it's not strong enough, and that image is going to focus before the fovea or after, and that's where we get our near farsightedness from. But the retina is where we see with color. So along the retina, and if you look on the diagram, it's the yellow, it's that nice yellow thin tissue on the back 2/3 or so of the eye, contains rods and contains cones, right? And these are the color sensitive and brightness sensitive. It's what lets us see our colors. So rods are going to detect brightness. We have 120 million of them. They're evenly distributed amongst the back part of your eye. Now the cones, on the other hand, if you look in that spot directly behind the lens on the back of the eye at the fovea, that's where we see color. That tiny little spot in the back of the eye, and there's approximately 6 million cones near the fovea. This is why our eyes are far better at detecting changes in light than it is color. Also think, when you wake up in the middle of the night, or if you wake up early in the morning and you open your eyes and your room's dark, you can't see color very well, but you can still detect shapes, you can still detect where things are, you can still see. It's just the colors aren't as sharp because we don't have nearly as many cones in our eye to help us pick up those colors the way we do rods. And with those cones, right, as we talk again about color here, we have 3 primary cones in our eyes: red, blue, and green. Right? So we have cones that are sensitive towards red light, cones that are sensitive towards blue light, and cones that are sensitive towards green light. And if you notice here, right, we kind of see where these wavelengths can overlap, right, and where we can see strong, the ability to strongly pick up certain colors, and also where the eye may get confused, and that's where some color deficiencies come from in the eye. So, for example, if you look at the green and the red waves that are on here, or the red graphs, I'm sorry, the 534 and the 564 for the wavelengths, those peaks are really close, which is why a very common type of color deficiency is red-green. And it's where people their eyes aren't sensitive enough to make out the difference between green and red. When they see it, the eye gets confused and it doesn't know what's being stimulated, so it just sees it all as one color. For example, there was an NFL game a couple years ago between the New York Jets and the Buffalo Bills. And the NFL has this great idea where they do color rush games where they let the teams just wear their primary color. So the Jets showed up in green helmet, green jersey, green pants. The Bills showed up in red helmet, red jersey, red pants. And people that had this deficiency couldn't tell which team was which because they couldn't see it, let alone you put it on a green field. So you have a green field with two jerseys that these people couldn't make out the difference between. Right? They couldn't tell very much. So that sensitivity in the eye varies. And the more sensitive it is, the more colors you can pick up. The less sensitive it is, the fewer colors you're able to pick up. And males in particular, see fewer colors than females do. On average, the male eye is less sensitive to color than the female eye is. Right? That's just the way that we're wired. It's, males don't see as many shades of colors. We still get the major players, but we don't get some of the specific shades the way that females do with their eye. All right, so every other color that we get, right? So if we see orange, if we see yellow, if we see, a color that's not one of these three as a pure color, it's based on specific stimulations to the cones. Right? So if you see something that's yellow, it's because a certain amount of the blue cones are stimulated, certain amount of green, and certain amount of red. Our eyes actually don't pick up a yellow wavelength. Rather, it's the different amounts of stimulation of those three colors of cones that allows our brain to interpret the color yellow.